This video is about inequalities generated by the knowledge of some moment about the distribution of a random variable. So we assume that some of the moments like mean or variance or let's say mean of x and sigma 2x are available, and we want to know what we could talk about probability. So is there any inequality or not? So two famous ones are Markov and Chebyshev inequalities. So far, we have learned how to calculate the statistics of a random variable from its distribution, which is if you, for a random variable, if you know the probability density function, let's say fx of x, you can calculate mean of g of x is going to be equal to integral of the value that g of x can take, and then say x from minus infinity to plus infinity dx. Now, so we know how to calculate. So the PDF or distribution here, distribution gives you moments. Now, if we know some of the moments, what we could say or talk about distribution. Let's say if I only know the mean of a random variable, or if I know the mean and variance, what I can do about that. So these inequalities will help us to give some answer. So if they have the mean or variance using the PDF of a random variable or CDF of a random variable, we want to know, we may not know the exact distribution, but because from the data you can calculate mean and variance, and you want to calculate some probabilities related to these random entities. So these two inequalities are the first one which were proposed, and we will prove them. So the Chebyshev inequality is applicable for the case that you have a random variable and the mean of it is given and its variance is given. And for some arbitrary number epsilon greater than 0, Chebyshev proposed this one. It says that the probability that random variable x is far away from its mean more than epsilon is smaller than this one. So if you have, this is, let's say, x, if this is, let's say, a mean of your random variable, and let's say this is mu plus epsilon, and this is mu minus epsilon. So you have some distribution here, which is centered around this point, and the variance of this cannot be like that. So it can be something like that, and its variance is like sigma. Okay. So we want to calculate probability that x is not in this interval, is in this interval, and this interval means this area, this shaded area. So Chebyshev inequality says that probability of being in this shaded area or being away from the center is always smaller than variance divided by epsilon to the power of 2. The proof is very easy. So basically, if I want to calculate probability that x being greater than this interval, that means that probability of this event. So probability of this event is integral of the PDF over this shaded area. So which is integral from minus infinity to point mu minus epsilon plus integral from this point to infinity, which is mu plus epsilon to infinity. So obviously here in this area and in this area I have 1, and 1 is always smaller than this function. In this area also I have 1, and this 1 is smaller than this one. So this integral is smaller than this integral, and this integral is smaller than or equal to this integral. So what happens is that this integral is from minus infinity to this point and from mu plus epsilon to this point, which is over the shaded area. But if I add another term, another positive term, integral from mu minus epsilon to up to mu plus epsilon of the same function, of this function, you see that this function is positive. So if I add this one to this integral, it becomes bigger, which becomes this one, because you have from minus infinity to this point, from this point to mu plus epsilon, and from mu plus epsilon to plus infinity. So this integral, because it doesn't have this term, it doesn't have this one, is always smaller than this one, because this integral has three parts. Two parts of it is this one, and it has a third part here, which is also positive. Now, this function, by definition, is, if you take this factor of 1 over epsilon 2 out, will be equal to the variance. So this is equal to this one. And the proof is complete. So this is called Chebyshev inequality in honor of Chebyshev. This means that the probability that the random variable x is away from the center more than epsilon is not more than variance divided by epsilon 2. So this says that the knowledge of the first and second order moment will produce an equality over the distribution of the random variable. Obviously, if this epsilon is a very a small number, this value becomes bigger than 1. So this inequality is not useful, because we already know that this guy is smaller than 1. But for very large values of epsilon, you will observe that the random variable cannot go away from the center. The probability of being away from the center reduces with inverse proportionally with epsilon to the power of 2 as epsilon increases. So usually this probability is far smaller than this one. So this is not a very tight inequality, but in the absence of any other knowledge about the exact distribution, this is a good inequality.